Hi, my name is Bahadur Ahmedov. In this video lecture, we are going to talk about the vector subspaces. We'll define them and we'll give an example of a vector subspace and example of the subspace which is not a vector subspace. So let's first of all define what are the vector subspaces. So the set of all the n-dimensional vectors is going to be called as a Rn space. And for example, the set of all the two-dimensional vectors is called the R2 space. And the set of all the three-dimensional vectors is called the R3 space consequently. And what do I mean by saying that the two-dimensional space or the three-dimensional space? I just mean that a vectors was the two components or the three components. So let's try to draw this three-dimensional space. So I've got the R3, which is going to be simply the three-dimensional space. So the X, Y, Y, X, and Z. So essentially, all of the vectors U with the components U1, U2, and U3 are going to be in this space, R3 space. So now what we want is we would like to choose some piece of this R3. So let's say this plane, okay? Any plane and it's three-dimensional, any plane which contains the 3D vectors or the vectors with the three components is going to be a subspace of R3 because it is some piece of the R3, some subset of the R3. And what we want is we would like to try to understand whether this subspace is the vector subspace or not. Okay, so it is essentially a very important question to work with the vector subspaces in linear algebra. And in order to work with them, we need to try to understand what they are. So let's give a definition of the vector subspaces. Subspace S is going to be called as a vector subspace of the Rn if it fulfills the following conditions. So if for any two vectors u and v, the following three conditions are fulfilled. So essentially, the sum of these two vectors should be from this subspace. So the multiplication of a constant to the vector should be again from the subspace. So it should not go out from the subspace, okay? Because you see the subspace is just some piece of this, some piece of this whole space, and the subspace should contain the zero vector. So we can try to we can try to explain this in this way. So let's say I've got the subspace S, which is going to be some piece of the R3. So it basically tells you that, hey, if you choose any two vectors, u and v from the subspace, their sum should be again here in the subspace. So you sum them, u plus v should be again here. It should not go outside the subspace, right? So outside the subspace, which is going to be same in our Rn, right? So the subspace is the some piece of the Rn, okay? So the vectors which are outside the subspace are still going to be in Rn, okay? But this is not going to be a vector subspace anymore. If a summation of any two vectors is outside this vector subspace. And again, the multiplication of any of these two vectors to the constant, let's say I'm going to multiply the u to the constant, should be in the subspace, and the multiplication of the k2 to the vector v should be again in the subspace. And it is important that the subspace should contain the zero vector. So this is, you will see in the next couple of slides that this is one of the important conditions to be a vector subspace. So let's give me an example of the vector subspace in R2. So let's say we're given two-dimensional space, so which is going to contain all of the vectors with the two components. So I would like to draw this line which is passing through the origin. So this is like this standard or the most popular line, y is equal to the x, right? So what I want is I would like to try to understand whether this is the vector subspace or not. And again, so let me define what is the subspace. So the subspace S is going to contains all vectors along this line. All vectors along this line. And obviously, this subspace is some piece of the R2, right? So all of the vectors, I've got this space of R2 with all of the vectors. And I'm just restricting some vectors. I'm choosing only some piece of the vectors which are along this line only. And I would like to try to understand whether this subspace is a vector subspace or not. So what does it mean? So it means that if I choose any vector along this line, a linear combination should be, so essentially the multiplication of this vector to any constant should be again from this line, so, which is true, right? So if you choose this vector, let's say with a component 1 and 1, if you multiply this to any constant, for example, just multiply this to the 3 or to the 4, it is still going to be in this vector, for example, 4 and 4. You can even multiply this to a negative number. It is going to be still along this line. For example, this vector is going to be -2 and -2, let's say, or -1 and -1, which is still going to be here along this line. So you can give another vector, for example, v vector. Let's say it's going to have the components -3 and -3. And this vector v is also going to be along this line, and any multiplication of this vector to the constant, to any constant, is going to be again along this line, right? And even more, this line contains the 0 point, which is the most important condition, actually. So the 0, 0 vector is also along this line. So this line or this subspace the subspace is fulfilling all of the three conditions to be a vector subspace. So we say that, hey, this S is a vector subspace. So it appears not all the lines in R2 are the vector subspaces. So let's just define a very similar line. So this is the line, which is just 2 units upper than the previous line, okay? So again, we can just try to think about this and discuss whether this line is a vector subspace or not by just choosing some vector and by trying to understand whether the scaling this vector is going to be along this line or not. So which seems that this is true because, for example, if you choose the u vector like this, the multiplication of this u vector is going to just change the length of this u vector. It's going to be either longer, either shorter, or it can go even to the opposite direction, right? So this is going to be, let's say, -u, this is 2u. You see, so all of the multiplications of a constant to the u is going to give me a vector along this line again. So you can choose another vector v, for example, along this line. So let's say this is going to be my v vector, which is going to be again along this line, and the summation of the v to the u is simply the summing their lengths, right? And you see, so they are going to be again along this line. But the problem is, so you can give an example of a linear combination of the two vectors or one of the vectors, which is not going to be in this vector subspace. For example, if you would just multiply the u to the 0, you would get this vector, which is going to be outside this line, right? So the 0 times the u is not in this line, is not in this subspace. So that's why the subspace is not going to be the vector subspace. So this is again a subspace of the R2, but this is not a vector subspace. Not a vector subspace. And if someone asks you to give an example of the vector subspace, you can give an example of a line from R2 or R3 which is passing through the origin, which is going to be an important condition, right? So analogously, we can define the planes in R3 to be a vector subspace or not. So let's say we are given three-dimensional space. The set of all of these 3D vectors are going to be the R3 space. So the R3 space contains all 3D vectors. So essentially all vectors with the three components. So the U, which is going to contain the X, Y, and Z. So what I want is I would like to choose some piece of the R3. So I would like to just choose the, let's say, XY plane. And I would like to try to understand whether this plane is a vector subspace or not. So this is going to be my subspace now. So, well, you can choose the two vectors. So let's say this is going to be my vector. Let's say this, let me call this vector as a 1, 0, 0 vector. And let's choose another vector, for example, this vector along the y-axis, it's going to be 0, 1, 0, right? And any linear combinations of these two vectors is going to be along this plane, right? Essentially, I can define this plane as a linear combinations of these two vectors, which I'm going to call as the I vector. So this vector is going to be called as an I vector, and this vector is going to be called as a J vector. And any vector along this plane, for example, this vector can be defined as a linear combinations of these two vectors. So essentially, I can just scale the I can just scale the V like this, and the summation is going to give me this vector, this green vector. So this green vector is going to be some constant times the I plus another constant k2 times the j, and which is obviously is going to be from the subspace, right? And at the same time, the subspace contains a zero vector, right? So if you multiply one of the vectors I to the zero, or the one of the vectors j to the zero, is still going to be inside the subspace. So essentially, this vector, the subspace fulfills all of the conditions, all of the three conditions. So that's why we call this subspace as the vector subspaces. And analogously, as we did for the lines, not any plane is the vector subspace. So for example, we can define a plane which is not passing through the origin. For example, this plane, which is going to be parallel to the xy plane, but this is passing through the z to be equal to the 2 point. So here is, I've got the z is equal to the 2. And this plane is not going to be a vector subspace. Not because the linear combinations of the two vectors along this plane are not going to be along this, is not going to be on this plane. So essentially, if you choose the two vectors, so let's say I'm going to choose the u vector, and you can choose the v vector, the summation of these two vectors, so it can be obtained by just creating the parallelogram, right? So this is going to be the summation of these two vectors, u plus v, which is still going to be on this plane. So essentially, you can multiply one of the vectors as a constant. You can just scale them. Let's say k1 times the u. Oh, this is the wrong color, right? K1 times the u is still going to be along this vector, along this plane. So some constant multiplied to the v vector is going to be along this plane, right? So there are lots of vectors, or lots of combinations of these two vectors, u and v, which are going to be on this plane. But again, we can find an exception. For example, if I would just multiply the u to the 0 or v to the 0, I would get this point or this vector, which is not on this plane. So that's why it's not a vector subspace. So this plane is not a vector subspace. And again, if you're asked to give an example of the vector subspaces, you can give an example of a plane in R3 which is passing through the origin. Essentially, so it should not be necessarily xy plane or zy plane. So this plane might be at some angle with the at some angle, for example. This plane is going to be like this, for example. But the main condition is that this plane should pass through the origin. Okay, and that is going to be a vector subspace. So we can give some sophisticated, like some a little bit more interesting examples of the vector subspaces or the subspaces which are not a vector subspace. So let's consider again the R2 space. So again, so the R2 is going to contain all of the two-dimensional vectors. So I would like to now choose some piece of the R2. So let's say I'm going to create a subspace by just choosing the first quarter. Okay, so this subspace S, is going to contain all vectors from the first quarter. And I would like to try to understand whether this vector subspace, this subspace of the R2 is the vector subspace or not. So this is S is the subspace of the R2, right? And I would like to try to understand whether this is the vector subspace. And I'm going to do the same thing as we did previously. So I'm going to define, for example, this vector. Let's say this is going to be the U vector, and it's going to contain it is going to be a 3-in-1 vector, right? So let's draw another vector here. So let's say I'm going to draw this vector with the components 2 and 3. So this vector is going to be 2 and 3. So please note that the summation of these two vectors is going to be again along inside this subspace. So for example, the summation is going to be 5 and 4 vector, right? So the summation is going to be 5 and 4 vector. So somewhere here, which is still going to be from the first quarter. And even more, the 0, 0 vector is along inside the subspace. So this is the 0, 0, 0 or 0, 0 vector. It's also going to be inside this subspace. So is it the vector subspace or not? So at the first glance, you can see that, hey, so all of the conditions are fulfilled. I can scale this vector. I can scale this vector. I can sum them and get the vectors from the first quarter, right? But again, we can figure out an example where a linear combination of one of the vectors is going to be outside this vector subspace, or outside the subspace, sorry. So if I would just multiply this vector U to the -1, then I would get this vector with the components -3 and -1. So this is minus U. So this vector is not from the first quarter, right? So just giving one counterexample is enough to show that the space or subspace is not a vector subspace. And again, it appears the first quarter is not a vector subspace. Even though it contains the 0 vector, even though that many linear combinations of the two vectors from this subspace are again the inside the subspace. Again, so this is not going to be a vector subspace because we can figure out an example of vectors which are going to be outside this vector subspace. And essentially, linear combinations of some of the vectors from the space are going to be outside this vector subspace. So please note that I found that I drew this vector a little bit wrongly. So it should be -3 and -2. But again, you can multiply one of the vectors to the -1, and it's going to be outside this vector subspace. So it appears we can define the vector subspaces for the matrices as well. So let's say we're given the set of all of the three-dimensional matrices, set of all three-dimensional matrices. So I'm going to redefine this again. So the set of all 3 by 3 matrices is going to define this. So one more time, set of all 3 by 3 matrices is a space. Okay, so I would like to choose some piece of the space. So let's say I'm going to choose only diagonal matrices. So I'm going to define the subspace as set of all 3 by 3 diagonal matrices. And all of this matrix and this subspace is going to be a vector subspace because all of the linear combinations of this diagonal matrices is going to give you again the diagonal matrix, right? So for example, I can give you this diagonal matrix. So let's make it 2 by 2. Okay, so let's say you're given 1, 0, 0, 2. You can add this into another diagonal matrix, 3, 0, 0, -3, for example. And the sum is going to be a diagonal matrix again, right? Because what is the definition of the diagonal matrix, by the way? So the definition of the diagonal matrix is that all of the components below and above the diagonal should be equal to the 0. So here you need to have the 0, and here you need to have a 0. So please note that on the diagonal matrix, we don't put the constraints onto the diagonal elements. So the diagonal elements can be any numbers, even zeros. But the main conditions is that all the entries below and above the diagonal should be 0. So I've got this two diagonal matrices. Any linear combinations of these two diagonal matrices are going to be again a diagonal matrix. I can multiply the first one to the k1, the second one to the k2, and if I would just add them, you would get a diagonal matrix that is going to be k1, 0, 0, 2, k1. And for the second one, it's going to be 3k2, 0, 0, minus 3k2, right? Which is again is a diagonal matrix. And even more, you can multiply one of the diagonal matrix to the 0, and you're going to get completely 0 matrix, so 0, 0, 0, 0. And if I say, hey, is it the diagonal matrix? Then yes, because all of the components above the diagonal and below the diagonal are equal to the 0. It's again a diagonal matrix. Another important subspace of the matrices, which is again a vector subspace, is the set of all of the triangular matrices. And again, so let's define the subspace as a set of all triangular matrices, and this is going to be again an example of a vector subspace. So because any linear combinations of the triangular matrices, so let's say the set of all upper triangular matrices, not the triangular, upper triangular matrices should be a vector subspace, is a vector subspace. So because you can take any two triangular matrix, let's say 1, 2, 0, 3, you can add this into another upper triangular matrix, so which is going to be minus 1, 3, 4, 0, 4. And the summation is going to be an upper triangular matrix. So it is going to be 0, 5, 0, 7. Is it the upper triangular matrix? Yes, because the definition of the upper triangular matrix is that all the entries below the diagonal should be equal to the 0. Please note that we don't put any constraint to all the entries above the diagonal. There might be any numbers, including zeros. So that is why if you just multiply one of the triangular matrices, upper triangular matrices, to the 0, you're going to get a completely 0 matrix. So this is 0, 0, 0, 0. And this is also going to be an upper triangular matrix, right? Because all of the entries below the diagonal are equal to the 0. And again, you see, so we can define the vector subspaces for the whole bunch of the matrices. So at the end of the day, we would be interested to construct this kind of vector subspaces for the matrices with the matrices. And in order to do this, we need to understand what is the vector subspace, what conditions fulfill the vector subspaces, and so on. So thank you very much for your attention. I hope that this video was helpful for you.